Hello, hello, hello. I have a pretty cool sequence. You probably heard of it before. Fibonacci numbers. I don't know if I'll spell it right. And they have a sequence that goes like this. It goes 1, 1, 2, 3, 5, 8, 13, 21, 34. And we can stop there. And the idea is that you take the two numbers before and you can add them to create the next number. In other words, if we have the nth Fibonacci number, it's always going to be equal to the one right before it plus the one right before that one. So, for example, this 8 is the 5 plus the 3. And this is the defining trait of the Fibonacci sequence. Now, I don't really know if this is why it's called the Fibonacci sequence, but you may have heard of another cool constant in math called phi, and maybe we can for today call them the PHIbonacci numbers, because there's a really cool relation between phi and the Fibonacci numbers. And phi it's usually like this. Oops, draw it good once and then it's like that. It looks like that. And it's 1 plus the square root of 5 over 2. Now, let's consider more generally. See, this kind of looks or resembles at least the quadratic formula. At least to me, it looks like a root of a quadratic. And so let's it's missing the plus or minus like the quadratic formula has. So let's consider instead 1 plus or minus the square root of 5 over 2. And if this is equal to x, let's find what quadratic has the roots of phi and the negative version. So I know that from this 2, I know that 2a is equal to 2, so a is equal to 1. I know that negative b is equal to 1, so b is equal to negative 1. And then I know that b squared minus 4ac is equal to 5, and we have b and we have a, so 1 minus 4c is equal to 5, so c is equal to negative 1 as well. And so the quadratic f of x that has a root of phi, the golden ratio, is x squared minus x minus 1. And you can verify this yourself with the quadratic formula. And so let's consider this this polynomial here. So we know that it has a root of phi, the golden ratio. So this means that when I plug in phi, I'm going to get 0. So phi squared minus phi minus 1 is equal to 0. And in other words, phi squared is equal to phi plus 1. That's a pretty cool property on its own, right? You square the number, that's the same thing as just taking it and adding 1. And you can try that on your calculator, actually. If you store this to, say, a, and then you square a, and then you take a, and then you add 1 to it, you're going to get the exact same number on your calculator. It's a pretty cool property. But, so we know that phi obviously is just, it's equal to phi by itself. And we know phi squared is equal to phi plus 1. Well, maybe you might be interested in, well, what's phi cubed equal to? Maybe we could simplify that some. Well, that's equal to phi squared times phi, which is phi plus 1 times phi. That's phi squared plus phi, which is phi plus 1 plus phi, or in other words, 2 phi plus 1. So you can cube the number. That's the same thing as just multiplying it by 2 and then adding 1. And let's do phi to the 4th. That's phi cubed times phi, which is 2 phi plus 1 times phi. So 2 phi squared plus phi, which is 2 times phi plus 1 plus phi, which is 2 phi plus 2 plus phi, or in other words, 3 phi plus 2. And there is a very cool pattern that is beginning to appear. Maybe you're not seeing it quite yet, so let me think maybe two more, and then I'm going to stop there. Phi to the fifth, that's phi to the fourth times phi. So phi to the fourth was 3 phi plus 2 times phi. So that's 3 phi squared plus 2 phi, which is 3 times phi plus 1 plus 2 phi, which is 3 phi plus 3 plus 2 phi. That's 5 phi plus 3. And last one, phi to the sixth is phi to the fifth times phi, which is 5 phi plus 3 times phi. So 5 phi squared plus 3 phi. It's 5 times phi plus 1 plus 3 phi. And this is 5 phi plus 5 plus 3 phi. That's 8 phi plus 5. And now I'm not going to actually show the calculation, but I'm just going to tell you that it does turn out that phi to the seventh is 13 phi plus 8. And it turns out that phi to the eighth is 21 phi plus 13. Now, I hope you see the pattern here. I really do. This is a really, really cool pattern. Powers of phi. Okay, look at. So, let me erase this. It makes it just a tad bit cluttered. I don't know why I wrote these over so far. This is phi to the seventh. This is phi to the eighth. And the phi squared is just phi plus 1, as we said above. Now look at, so phi squared is phi, this is really a 1 phi plus 1, okay? We have a 1 phi plus 1. Now, phi cubed is 2 phi, 2 phi. I'll do it in red, I probably should do it. It's the 2 phi plus 1. This is 3 phi plus 2. This is 5 phi plus the 3. And 8 and 8 and 5 and 5 and 13 and 13 and so on and so on. So you get the idea. And probably you could guess by now that phi to the ninth is 34 phi plus 21. So these coefficients, at least so far, appear to be given by the Fibonacci numbers. That's why I called them the PHIbonacci numbers, because they're related to powers of phi. It was kind of a bad joke, but yeah, that's the idea, is that if we were to generalize this, we could say that phi to the n, this would be my claim, is f sub n, where f sub n is the nth Fibonacci number, times phi, plus the n minus 1th Fibonacci number, f sub n minus 1. And we can see that here, right? For example, I'll just pick phi to the fifth. Phi to the fifth is, we're claiming, f sub 5 phi plus f sub 4. And we look at this and we say, okay, the fifth term in this sequence here is this 5, which is exactly what we have here. We have a 5 here and a 5 there. And then the fourth term is this here. So we would say that that's 5 phi plus 3. And this is exactly what we got down here. That's pretty cool. And so we can generalize this just like how we've done. And now we haven't actually proven it, but almost always a technique, a proof technique that always, well, not always, but it will almost always work when you kind of see patterns like this. And it's a really powerful technique when you see patterns, because it's induction, right? We can we can do a proof by induction. And why is induction so powerful here? Well, with induction, you don't have to actually give reason to why you saw the pattern or anything like that. You just have to recognize that there is a pattern, and then you can just use induction and then prove it from there. So there's no reasoning behind why the pattern is there. You just say, oh, the pattern's there, I'll prove it by induction. You don't have to give any motivation behind the pattern, which is it's powerful, and it proves it just as valid as maybe proof by deduction instead. That does require more intuition. So we're going to do this by induction. It's a really, really simple proof. We start with the base case. Like always, the base case is that, we would start really with, we really started with phi squared. So our base case is n equals 2. And we know that phi squared is phi plus 1 because it's a root of the quadratic it's the root of the quadratic x squared minus x minus 1. So when we plug in phi, we get phi squared minus phi minus 1 is equal to 0. Rearranging phi squared is equal to phi plus 1. So the base case is true. And then now we assume we assume that this statement here is true for n somewhere between, greater than 2, because we already did 2, and we know it's true. So greater than 2 up to or equal to n minus 1. So from 3 to n minus 1, we assume it to be true. And then now we need to prove it for n. And we can use this step here where we assume it to be true is called the inductive hypothesis. And we can use the inductive hypothesis in the actual proof for n, and it's not circular or anything like that. So we want to find out what phi to the n is. Okay, now it's almost always a good idea in any inductive proof to use the inductive hypothesis in the actual proof part of the proof, not the base case or anything like this. So we know that phi to the n, I want to break this down into phi to the n minus 1 times phi. And we know by the inductive hypothesis that phi to the n minus 1 is f sub n minus 1 phi plus f sub n minus 2 by the inductive hypothesis times a phi. And so this is f sub n minus 1 phi squared plus phi f sub n minus 2, which is f sub n minus 1 times phi plus 1 plus phi f sub n minus 2, which is phi f sub n minus 1 plus f sub n minus 1 plus phi f sub n minus 2. This is phi times f sub n minus 1 plus f sub n minus 2 plus f sub n minus 1. Now, this is phi times, now this in here, we said right from the get-go, that's the defining trait of the Fibonacci sequence itself. The sum of the two previous terms is the term to the right. So f sub n minus 1 plus f sub n minus 2 is just f sub n plus f sub n minus 1. And that's exactly what we wanted to show. So quite easily done. And now we know that this is true for all n. We could say it's true based on this induction for all n between 2 and n. Or I guess I should say for all k between 2 and n because we already used n there. Now, another thing I want to notice is, well, actually, I'm going to do this first. See, we know that this is a recursive way of getting the nth Fibonacci term. In other words, we can generate as many Fibonacci numbers as we want using this formula here that I've underlined probably 7 times, but we have to know the 2 previous terms in order to do that. And, you know, say we wanted f sub 1,000, for example. All right, it's pretty hard to find what f sub 999 and f sub 998 are. So it would be nice, at least, if we had an explicit formula for the nth Fibonacci number, and that's what I'm going to derive. The idea here is that, see, we've only discussed phi so far. We've only discussed phi, which is 1 plus the square root of 5 over 2. But, and that's the root of the quadratic x squared minus x minus 1 equals 0. But we got to remember here that there was another root. There was another root, 1 minus square root 5 over 2. And since it's the root of the very same quadratic that phi is, then it must have all the same properties that phi has. So, in other words, let's call this root 1 minus square root 5 over 2. Let's call it sigma. It doesn't really matter what you call it, but I'm going to call it sigma. And so sigma would also have this same property here that we proved. In other words, we know that phi to the n is f sub n phi plus f sub n minus 1. But it's also true that sigma to the n is f sub n sigma plus f sub n minus 1. And now we can subtract these two equations, to get rid of this f sub n minus 1 term. And we get that phi to the n minus sigma to the n is, sorry, that's f sub n phi minus f sub n sigma. Or in other words, f sub n times phi minus sigma. And look at that. We can just solve for f sub n. In other words, the nth Fibonacci number. It is given by phi to the n minus sigma to the n over phi minus sigma. And you might be thinking, well, what the heck? It looks like all variables. Well, no, those are all numbers in there, except for the n. Phi is a number, 1 plus square root 5 over 2. Sigma is a number, 1 minus square root 5 over 2. They're all numbers in there. So, maybe you want to replace what phi and sigma are. You might want to note that phi minus sigma is 1 plus square root 5 minus 1 minus square root 5 over 2, which is, the 1's cancel, and then we have 2 square root 5 over 2, so just a square root 5. So phi minus sigma is just square root 5. So if we were to replace this without the variable-ish looking notation, we would get that f sub n, the nth Fibonacci number, has an explicit formula, and that explicit formula is 1 plus square root 5 over 2 to the n minus 1 minus square root 5 over 2 to the n all over square root 5. And that's an explicit formula for the nth Fibonacci number that does not rely on any previous terms before it. So we could easily find f sub 1,000 now without knowing f sub 999 and f sub 998. And that's pretty cool. One other kind of tidbit I just wanted to share. And this probably isn't all that practical, but I just kind of was thinking about it, and I said, well, that's kind of cool. I didn't really know that before. But see, we know phi squared is equal to phi plus 1, which I'm going to write it as phi to the 1 plus phi to the 0. Okay, now we also know that phi cubed is, well, it's phi squared times phi, which is phi plus 1 plus phi, which is 2 phi plus 1, which is that we can break this up as phi plus 1 plus phi, which this part here is phi squared, and then we just have phi to the first. So let's do it for phi to the fourth. Phi to the fourth is, I'm going to break it up as phi squared times phi squared, which is phi plus 1 times phi plus 1. So that's phi squared plus 2 phi plus 1, which is phi plus 1 plus 2 phi plus 1. And if you recall from before, phi cubed, we showed it up here, was the same thing as 2 phi plus 1. So this here is phi cubed, and this here is phi squared. So phi cubed plus phi squared. So it's looking like, oh, well, it's, I'll write it here. It's looking like phi to the n is the sum of the two exponents before it. In other words, phi to the n minus 1 plus phi to the n minus 2. And, this holds, well, it doesn't hold for, I'm curious now, because, we know we have this polynomial x squared minus x minus 1 equals 0, and we know that then phi squared minus phi minus 1 is equal to 0. So I can add 1 to both sides and factor out a phi. So phi times phi minus 1 is equal to 1. See, I added that 1 over there and then pulled out a phi on the other side. So we can divide both sides by phi since it's not equal to 0. So we get phi to the negative 1 is phi to the 0, or just, well, okay. Phi to the negative 1 is equal to phi minus 1. So, yeah, that works. See, because now phi to the 1 is, if I add this 1 over here, the 1 is really phi to the 0 plus phi to the negative 1. So it even works for phi to the 1. You can, I don't know why you would want to write phi to the 1 as the sum of two separate things, but that's just kind of cool that works there. So yeah, the claim that I want to prove is that phi to the n is phi to the n minus 1 plus phi to the n minus 2. And this is probably the easiest induction proof you'll ever see in your entire life. We want to show the base case. The base case is the lowest n that we wish to prove it for. And I'll start with n equals 1 because that's what we have here. And we just showed that this base case is true right here. So it's true. Now we're going to assume true for n somewhere between 2 and how did I write it up there? I wrote so n is somewhere between 2 I shouldn't have wrote that. I should have used a different variable like k or something, because obviously n can't be less than n minus 1. That's not possible. But so assume true for some k. I'm just using k as a dummy variable between 2 and n minus 1. Okay, so, and now we want to prove for k equals to n. In other words, we want to show it for an arbitrary n. So this is super easiest induction proof you've ever seen in your life. We know phi to the n is phi to the n minus 1 times phi. And by the inductive hypothesis, this part is phi to the n minus 2 plus phi to the n minus 3 times phi, which is phi to the n minus 1 plus phi to the n minus 2. And that's literally it. That's the proof right there. I don't even know if I'm going to write, I'm not even going to write QED there because that's insanely easy. But that covers some pretty cool parts of the Fibonacci sequence, and you can explore it for yourself. Oh, and if you're interested, this formula here, the explicit formula for the nth Fibonacci number, is called Binet's formula. If you want to take more of a look at it, I think